Math 1314, Tyler Junior College, Section 4.1, Exponential Functions, Application, Compound Interest, Part 1. At some point, everybody wants to retire. And in order to do that, you have to have enough money to live on once you stop working. So how do people do that? Well, the standard way is to put money into some sort of retirement fund over the course of your career, so that at the end, that money, along with the interest that has been earned, is enough for you to live on for the rest of your life. There's a few ways to look at it from the perspective of an annuity, from the perspective of something like a 401k, but we're not going to get into all those details. For those details, I would recommend taking a business math class or some sort of accounting class. I'm just going to kind of show you the basic idea behind the thing. Suppose you invest $10,000 at 5% interest, compounded monthly. I'll explain what that means in just a moment. What is the future value of your investment after 20 years? And we're going to do a follow-up. What if it were compounded weekly, daily, and continuously? And by the way, this continuously is why there's going to be a part 2. Well, first let's take a look at the formula we're going to use. The formula for compound interest is usually written this way. A equals P times the quantity, 1 plus R over N, all to the NT power, where P is the principal, how much you invest at the beginning, which in this case is 10,000. R is the interest rate, which is 5%, but we'll have to write it as a decimal. T is the number of years, which in this case is 20. But the one that some people have trouble wrapping their mind around is the N, which is the number of times per year interest is compounded. It's rarely ever given as a value, but usually in the form of an adverb. In this case, that adverb is monthly. If N is measuring the number of times per year something is happening and it happens monthly, then it happens 12 times per year. When we get to weekly, that will be 52 times per year. I know a year isn't exactly 52 weeks, but that's the number we're going to use. Daily, we're going to use 365 times per year. I know, leap years, but let's not worry about that. And we'll see what happens. So let's do the first part, where we're investing $10,000 at 5% interest compounded monthly for 20 years. Needless to say, this will require a calculator. We have P equals 10,000, our principal that we're investing. R is 5%, but you don't do math with decimals. Decimals describe things. You do math with their you don't do math with percents. Percents describe things. You do math with their decimal equivalents. To turn a percent to a decimal, locate its currently existing decimal and move it 2 places to the left, which in this case would give us an interest rate of 0.05. Since percent literally means per 100, that is 5 per 100, or 5 100ths. Our time is 20 years, and because we're compounding interest monthly, then N is equal to 12. And what it means to compound interest monthly is this. Over the course of a year, we have a 5% interest rate. Imagine taking that 5% and dividing it by 12, and then each month I calculate that part of the interest and add it on. So why not wait until the end of the year? Because the sooner you put on interest, the sooner it starts earning interest, hence the word compound interest. If we were to set this up, we would get that our future value, and I'm sorry, I never actually said that A was the future value, because A is the natural choice for the phrase future value. I didn't get to make that decision. Future value. All right, so it's our principal, 10,000, times open parentheses, 1 plus the interest rate, which is 0.05, over the N, which is 12. There's the 5% interest getting divided into 12ths. And the exponent is the N times T, so 12 times 20, which represents the number of times you get interest over the course of the investment, 12 times a year for 20 years. Now there's a few ways to go about doing this in a calculator, in bits and pieces. Let me calculate this, let me calculate that, and then you just push it as far as you can. But if you have the technology, I would just put it in your calculator all in one fell swoop. If you're going to do that, the trick to doing that is using an extra set of parentheses around the multiplication problem, because otherwise your calculator's order of operations will not give you the value that you're expecting. If you have a display calculator, it's easy. You type it just like you see it. So I'm going to do a one-line calculator. Now, in most one-line calculators, there's an exponent. It may look like this. It may look like a little caret symbol, which looks like that. But it's your responsibility for knowing where the exponent button is on your calculator. There's really no trickery to putting this in a one-line calculator. Just go left to right and be sure to use parentheses around the multiplication problem in the exponent. Otherwise, it won't put the 20 in the exponent where it belongs. So here it goes. Let's focus on this. All right, so we're going to start with 10,000 times, open parentheses, 1 plus 0.05 divided by 12, close those parentheses, and then raise it to a power. Open the parentheses for the multiplication problem in the exponent, 12 times 20. Close that parentheses and then press equals to finish everything. And if I put in everything correctly, looks like the answer is to the nearest cent, $27,126.40. Let's do it in the display calculator just to see if we get the same answer. For the display calculator, it's a little bit easier because we see what we type. 10,000 times parentheses, 1 plus 0.05 divided by 12, close parentheses. Is that really a plus sign? Hold on, folks. I think I pressed the wrong button. I did. Okay. I'm not sure what I pressed, but I was pressing buttons blindly. So, all right, so 10,000 times 1 plus 0.05 divided by 12, exponent. Now this calculator's exponent button is here. And when I press it, it puts an exponent there. And because it knows everything's in the exponent, I don't need parentheses, but I always like to play it safe. So we'll do 12 times 20, close that parentheses and press enter or equals, and we get the same answer we got before, $27,126.40. So let's go write that answer down. That's not bad. We more than doubled our money. We had to wait 20 years for it to happen, and we needed $10,000 up front, but you gotta have money to make money, or a long time. But still, that's an extra $17,126.40 on top of what we started with for just letting the money sit there. But why discuss compounding more frequently? Because banks are competitive. Banks cannot control how much you're going to invest, nor can they control how long you're going to invest it. Now, they kind of have some say about the interest rate, but that's usually established outside of their parameters. But they can't control how frequently they offer you interest. Is there an advantage to getting interest more frequently? Yes, there is. You actually get more money in the long run. That can be proven. But for the rest of these, for weekly, we would just change n equals 52, and for daily, we would say n equals 365. So the setups would be pretty much the same. For weekly, our future value would be 10,000 times 1 plus the interest rate, 0.05, divided by 52, and in the exponent 52 times 20, which will be a little bit, it will be more than that. And then for daily, we'll do the same thing, except we use 365 instead of 52. Now, as I'm writing these, I invite you to pause the video and see if you can put these in your calculator and get the future values. And let's see how much better it will be if we go weekly instead of monthly. All right, I made the changes. All right. Again, I invite you to pause the video and put both of these in your calculator just to practice using the calculator. For weekly, and I forgot to write weekly over here. I know it's weekly because our N was 52. For weekly, the future value is $27,169.76. So is it more? Yeah. Is it a lot more? No. But at the end of 20 years, if I offered you one of these two checks, I think I know which one I'd take. And then for the daily, maybe that'll be a lot more. let's see, 365. In this particular calculator, I can just copy the original problem and edit it. But, you know, if you don't know how to be fancy with a calculator like that, just retype the whole thing. And if it's a display calculator, look at it and make sure it's typed in correctly. But for the daily, where they say at the end of each day, we're going to calculate the interest you've earned on that one day and add it on to your principal, $27,180.96. And again, it's not significantly more, but if I offered you one of these 3 checks, we would all take this one. If there were no strings attached, of course. But what about this continuously thing? What's going on there? Well, if more frequent interest compounding gives you more money, then why stop it daily? How about I calculate interest every hour, or every minute, or every second, or twice a second, or 10 times a second, or 100 times a second? We're talking about really small amounts, but a lot of them, and the net result is this value keeps going higher and higher and higher. Well, will it get infinitely higher? And the answer is no. There's a limit to how much this would be worth if you just kept increasing the frequency with which interest was compounded and added to your principal. And it's called continuously compounded interest. It is that limit. In the next video, I'm going to kind of show you where that formula came from. You won't have to derive it, but it's pretty interesting because it has something to do with the number E.